to do this? How do they know to start dividing? How do they know when to stop dividing? And that's really the bulk of what I want to really get across today is you saw those pictures that we drew, and yes, those are important. But when you start to think and we start digging into things like cancer, any sort of disease or disorder that affects the growth or lack of growth in cells, we need to identify what is happening. For example, if you have cells that are too small and divide when they're too small, what do you get? Does anybody know? And you've heard of it. It's known as leukemia, right? Or you get some cells that just keep dividing and dividing and dividing with no apoptosis. What do we call that? That's cancer. And so then the question becomes, all right, here's my question to you. And we all agree that cancer sucks. And there's only some kind of primitive ways we're still dealing with it. We're still investigating it. There's really two ways that we're combating cancer right now, is we're trying to either just use radiation and destroy everything in the path, or we use chemotherapy, which targets rapidly reproducing cells, but cannot differentiate between cells that are not cancerous, but they're rapidly reproducing as well, like skin, hair, nails, stuff like that. That's why when people are on chemotherapy, they get incredibly sick. So it's kind of like treating a poison with a poison. And I think we can agree that if we could figure out how to pinpoint the communication, the targeting communication of those cancerous cells, whether we can turn something on or turn something off, then that would be awesome. For example, if I were to say something to you like this, if you were smart people and you said, well, cancer cells keep rapidly reproducing, they keep dividing, what's one way to stop them from dividing according to this picture? What could we stop from being built? Microtubules. There are drugs that prevent the buildout of microtubules. There are drugs that can actually stop the actin filament from occurring. So what it does is that you kind of get this kind of discombobulated cell, but it's not going to complete itself and keep becoming immortal. Or what are the communications that are turning off the apoptosis signals? How do we turn them back on? And you know why I'm setting you up like this? Because when I see you on Thursday, you are going to have to try and save Wiggles the dog. Wiggles has cancer. And you are going to try and figure out which cellular signals do we turn on, which cellular signals do we turn off, and based on how those premises work. So it's really important that you pay attention to what I'm saying here today. Our third and final cell-mediated pathway. We did ligand-gated ion channels, which is one-to-one synaptic signaling. We did G proteins, which we said are the most common, but only have one message, one response, correct? Now what we get into, and this is where you need to start taking notes, you get your phones ready here. Now we get into our third, what we call tyrosine kinase receptors. Now let me tell you about tyrosine kinase receptors. These are essentially relegated to cell division. And this falls under the parameters of what we call paracrine signaling. So earlier when I was talking about why cells divide, one of the reasons is that they're signaled to divide from a damaged cell. Whenever you bump, you get a bump, a bruise, a scratch, anything like that, those damaged cells will release what we call growth factors. And those growth factors, in this case, those are your ligands. A growth factor sometimes could be normal. It could be human growth hormone, that hormone we talked about. Or it could be other cells releasing these messages for the surrounding cells to divide. We call this paracrine signaling. One cell communicating to many around it. So those cells start to divide. How many of you ever had a scab somewhere and your parents tell you what? Don't scratch at it. Don't pick at it. Why? Because underneath that scab, you've got cell division happening. And if you keep picking at it, you're not going to allow that division to complete, and you're going to get scars, which is just fibrous tissue. It's not cells. So it's not going to perform the way it should. So how do these receptor or tyrosine kinase receptors work? This is where it gets a little clunky, so just stick with me for a second. Number one, we know our ligands now. Those are growth factors. These are going to signal cell division to occur. But because it's paracrine signaling, you have to have two or more for this to actually happen. All right? Because it's paracrine signaling, that's why we have 2 or more. And what you notice is that these tyrosine kinase receptors, before they're actually signaled by the growth factors, notice how they're separate from each other, which means they're inactive. But as soon as those growth factors connect, what does it do to the protein? You all know this. Changes shape. So as soon as it changes shape, reveals these binding sites, both of these tyrosine kinases, they do this. They change their shape, and then they come together. We call that a dimer. And dimers are absolutely vital for this. Essentially, it's the same analogy I've been using. Once the dimer forms, now they activate all of the binding sites of these tyrosines. Tyrosines are amino acids. And they're these little binding spots, and as you notice, each side has 3 of them. And this is going to make sense in a second. So once the dimer is formed, now all of these tyrosines can be phosphorylated. ATP can add phosphates and energize this whole thing. So all of a sudden now, the growth factors connect, forms a dimer. Those tyrosine amino acids, you see in this case 6 of them, are all phosphorylated at the same time. Why do you think there's 6? This is an interesting perspective. Go back to your picture on prophase for a second. How many different things are happening during prophase? Simultaneously. You have your centrioles building microtubules, that's 1. Your nuclear envelope's disappearing, that's 2. Your chromosomes are condensing because those histones are starting to wrap, that's 3. So we could do this all day, right? What we're noticing is that we have multiple things happening simultaneously, which means you have to have multiple messages being sent simultaneously. Different messages to different areas, different receptors, but multiple messages sent simultaneously. So tyrosine kinase receptors are the best form to do that, because each of these tyrosines that are phosphorylated, now they can activate a very specific pathway. So this is, remember, this is reception. But once these cellular responses, or those signals are sent, now we're into the transduction stage. And so to get your histones to wrap up your DNA, that's one transduction pathway. To get your nuclear envelope to disappear, that's a different transduction pathway. Same thing for centrioles. So they all have their own pathway. So each of these tyrosines are going to initiate a different cellular pathway to get these things happening simultaneously. Everybody with me so far? I don't know if I'm explaining that okay. Yeah.
So does that mean they always have like 6 tyrosines, or will that just be...
Well, in this case, now keep in mind, you have hundreds of these all over the place.
Okay.
Now, here's one, and that kind of makes me think of something that I want you to jot down here. Which cells have tyrosine kinases? Because we said ligand-gated ion channels were only nerves. G proteins are about 80% of our cells. Not all of them have G proteins, because some of them have ligand-gated ion channels. Who has these?
Somatic cells?
All of them. Somatic cells. Any cell that's going to divide has to have these. So they're very, very common. So every cell has these. And the other thing I would tell you to add is there is no secondary messenger here. G proteins, we had cyclic AMP. Ligand-gated ion channels, we had calcium. In this case, there is no secondary messenger, just for normal cell division. Now, apoptosis there will be, but in this case, no secondary messenger. Okay, so here's my follow-up, and this is where we're going to get a little bit more into depth, but because it's a little heavy, I'm not going to go too far too fast today, because I'm going to eventually pull back and let you work on your labs and start working through some of those practice problems I gave you. But when you start looking at some of those practice problems, some of these words are going to look like a foreign language to you. So let me walk you through these. Because what we have to look at now is when we get to, I'm going to come back to this on Thursday, when we get to this component here, I know there's a lot that I'm passing by, is that we have to look at what are these signaling molecules. And ladies and gentlemen, all of these factors, whether it's the disintegration of the nuclear envelope, centrioles, microtubules, you name it, whatever it is, it's being regulated by proteins known as kinases. You've already heard this, haven't you? Kinases are those transduction proteins, those relay proteins. However, in this case, cell division, what actually makes this move forward are little tiny proteins called cyclins. Okay? Cyclins. And let me warm you up to this. So, all of these proteins that play, these kinase proteins that play a role in signaling all these different things happening in cell division, we call these CDKs. Cyclin-dependent kinases. Which means the kinase won't send the message unless it's activated by a very particular cyclin. For example, if you look up here for a second, G1. All right, we know that G1 is just normal growth and development. Well, what regulates the communications to maintain the G1 state? Cyclin D and E, and it has to connect to CDKs 4, 2, and 6. Now, you don't have to memorize that. I'm just showing you for effect. But it's showing you in G1, you need that combination. So in G1, we should expect to see a quantitative rise of D and E. So if all of a sudden I see a drastic drop in D and E, my cells are no longer in G1. They just keep repeating. See, we can measure all of these. Now, one thing I want to point out, make sure you get this. Cyclins rise and fall throughout the cell cycle. All right? They will stay at basement levels, and then once division kind of gets closer and closer, they rise. However, your CDKs are always there. They are consistent. They do not fluctuate. So what we're showing you here is how these aspects are regulated. And I can go right down the list, and you can see them now. Your S phase, cyclin A and E, CDK2. G2, cyclin A, CDK2. And then I go down here, mitosis, cyclin B, CDK1. So why do we care to know these? Because if we're trying to stop or amplify something, doesn't it help to know what's throwing out those communications? Right? So tomorrow or Thursday, you're going to be propositioned with, hey, how do we turn on or off CDK2? What should we do? How do we turn on CDK1? Right? So these are the things that we're going to focus our attention on. And if you know that maybe you want your cells to divide, but they're not, right? And you have CDK1, but for some reason you don't have cyclin B and you want your cells to divide, what would you do? What would you do? If you know cyclin B is what triggers nuclear division, and you don't have cyclin B, what should we synthetically give you? Cyclin B. See, that's why we measure these things. That's why we have to know these things, because we talk about cell division and the regulation of it. Well, the definition of cancer is a severe failure in the regulation of these things. So we have to identify where those failures are happening. So take a look at this. And I know you got this your freshman year. All of these regulations are there for safeguards. So you notice throughout the G1, SG2, and then into mitosis, you have G1. So right here, all the cells are under normal growth and development. Then once they kind of hit the end of their life cycle, they're going to hit what's called a G1 checkpoint. And what you're going to find here is that the G1 checkpoint, like everything else, is regulated by a certain CDK with that cyclin. And if all of a sudden that cyclin is there, what do you think is going to happen? It's going to move forward, right? But if that cyclin isn't there, it's going to go into a G0 state, which just means it's going to reverberate back to a non-dividing state. So once it passes the G1 checkpoint, now that signal is to proceed forward, go through the S phase, and then go through the G2 phase. But you notice something interesting about the S phase. What don't you see? You don't have a checkpoint. Now, most people would say, well, that's stupid, isn't it? Because we know during DNA replication, that's where you're going to get the most amount of mutations and errors in the reading, which is what leads to mutations. See, you think mutations are bad. I think mutations are awesome. Sometimes detrimental, yes. But none of us would be here if it weren't for mutations. So if we had a regulatory system here, none of us would be here. So it doesn't make sense to have that checkpoint. So that's why that checkpoint doesn't occur until you get to the G2 state, which means, have I doubled all the organelles? Is the DNA doubled? And we're ready to move forward. Yes? Okay? You can now pass go, and you move right into the metaphase. All right, and we're going to come back and talk about that a little bit more later, because this M checkpoint is known as the metaphase checkpoint. Why would we care only about metaphase?
Before the separation.
It is before the separation, yes, but what are we regulating? What are we checking on in metaphase? Because if you don't check on it and something goes wrong, this is bad.
It's not chromosomes lined up.
Yeah, it's not the chromosomes lined up, but they're equally connected on both sides. Because if I take this one away and I start to separate, this one's going to have too much DNA on that in that cell, right? And this one's not going to have enough. So we start looking at that. That's going to ensure that there is proper connection. So all of these things right here that you're seeing is constant regulation. Now you'll see this right here. Now, of course, you don't have to memorize this. I will give this to you at any point, but this right here is showing you how all of this is regulated. And this is why I wanted you to know what was happening in each of these phases, because it gives us insight of what's regulating them. Okay? Now, what we're going to end up doing is we're going to start looking at apoptosis, the cell signaling of the end of a life cycle. But we're going to do that on Thursday. So this is what I'd like you to do. Take a look at those practice problems for me. Turn to the back page. All right. And go ahead and look at question number 17. I'm sorry, no, 19, my mistake. It says, which of the following is a protein maintained at constant levels throughout the cell cycle that requires cyclin to become catalytically active? What would you put? That's a CDK, very good. Now go back up to 17. The cyclin component of MPF is destroyed at the end of this phase. Well, some of you are like, well, wait, what is MPF? Take a look at this. When you look at the rise and fall, remember I said CDKs are always consistent. But as you can see right here, the overlap of interphase, at the end of interphase, your cyclin increases. And then mitosis is, you're going to see this rise of what's called MPF, mitosis promoting factor. That's what that stands for. And it's just all of these proteins that are going to signal all of those factors that we just talked about. The nuclear envelope, all those things. And then at the end of telophase cytokinesis, you notice your cyclins and your MPF drastically drop back into basement levels. And then they just flatline and then eventually build. And so this is, again, all of your regulatory things. So if you were a cytologist or an oncologist and you're studying cancer, think for a second, what things can we measure out of all of this? Can you measure CDKs? Yes or no? No, because didn't we just say they're constant? But can we measure cyclins? Specific cyclins, right? What else can we measure? We can measure MPF. Anything else we can measure? Growth factors. We can measure those too. Because sometimes cells don't give off growth factors. Or we can also go back and say, well, if we just wanted to cut the head off the snake and say, well, why didn't we just do this? If we wanted cells to stop dividing, what else would you do? Wouldn't you just block the signal reception here? Jam the signal, competitively inhibit that connection? So this is what I'm trying to get you to think about, is knowing the basics, but then how can we manipulate this? So the rest of the period, last 15 minutes, what I'd like you to do is finish that lab. I'm going to collect that on Thursday. That will be a grade. All right, so make sure that's kind of that mini lab, that chi-square, what we did today. Or if you're done with that, or you feel